One. Morning, everybody. I'd like to thank everybody for attending today's webcast, Understanding Connectivity, both Reservoir and Digital, how cloud-based software and digital platforms are modernizing tracer diagnostic studies. This is brought to you by Journal of Petroleum Technology and sponsored by Tracerco. Today's speaker, Dr. Sudiptya Banerjee, is a petroleum engineer from Texas A&M and Global Technology Manager at Tracerco. In his role, he's responsible for the reservoir tracer technology portfolio and for creating and launching new technologies addressing operator needs. With over 15 years' experience, Dr. Banerjee's global experience ranges from Alaska to Saudi Arabia, implementing technical solutions in enhanced oil recovery and hydraulic fracturing operations. He has multiple patents, awards, and has presented conference papers and lectures on well design as part of the SPE short course program. Oilfield tracers have long been a foundational tool for understanding fluid flow and reservoir production, providing essential information for an informed drilling, completion, and production program. Today's topic will cover operator struggles with the limitations of traditional tracer studies and the slow process of laboratory analysis, data management, and data visualization in a market that rewards rapidity and flexibility. Raising the bar to a new level of efficiency and performance has a clear value. But to achieve the desired outcomes, the collection, analysis, and sharing of data needs to be faster and more error-proof than current systems allow. In this webcast, Dr. Banerjee will share his knowledge of oilfield tracers to explain the technical strengths and weaknesses of various commercial products, walk listeners through how the tracer data is analyzed to illuminate production and communication trends, and will discuss Tracerco's new Insights platform. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple application engagement tools that you can use. All of the tools are resizable and movable, so feel free to move them around to get the most out of your desktop space. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A engagement tool. We'll try to answer these during the webcast, but if a fuller answer is needed or we run out of time, it'll be answered later via email. Additional help materials are available in the resource list. A copy of today's presentation will be available after the event. For the best viewing experience, we recommend using a wired connection and closing any programs or browser sessions running in the background that could cause you issues. This webcast is being streamed through your computer, so there is no dial-in number. For the best audio quality, make sure your computer speakers or headset are turned on and the volume is up so that you can hear adequately. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. You can find additional answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of this webcast will be available from the JPT website and can be accessed using the same audience link that was sent to you earlier. And now, it's my pleasure to introduce Dr. Sudiptya Banerjee. I would like to
Good morning, everyone.
I'm sorry. Go ahead, please, Doctor.
Sorry. Good morning, everyone. I'm excited to speak to you today. If you are not familiar with Tracerco, my employer, it seems appropriate to just give them a quick introduction as well. Tracerco is a world-leading industrial technology company that has developed and used tracer diagnostic and measurement tools in a number of different industries, including outside the oil field. Behind the scenes, it's done a great deal to improve safety, security, and technical understanding through activities as varied as fuel security programs for organizations like NATO, cutting-edge radiation monitors, and, of course, oilfield operations. The Reservoir Group, where I work, has over 40 years of experience helping oil companies understand the movement of fluids within their reservoirs and help them make informed decisions that affect their drilling, completions, and production strategy. Now, the presentation today is going to start with what is probably the most basic question, which is, what is a tracer and why should we be using them at all? Tracers are any of a variety of different fluid markers that allow us to distinguish where a given fluid in the reservoir originates from and how the interaction of the well and the reservoir is causing that fluid to move. The tracer studies can focus on just a single well where the tracer is delivered through and produced from the same completion system, or it might focus on how the drainage areas of different wells interact or even how the fluid front of a water or gas flood is traveling through the reservoir. Now, over the years, a number of different things have been used as oilfield tracers. Radioactive isotopes were some of the first reservoir tracers, though the risks to the people and the environment have caused them to be replaced by safer alternatives. You have tracers on opposite ends of the technology scale. The very simplest might be something like dyes or pigments, which have been used as tracers. And then on the sort of high technology side of things, you've got items as complicated as lab-built nanoparticles. A number of biological agents, usually some variation of DNA, have been used as oilfield tracers, as have passive chemical markers. Now, a lot of things can be used to try and mark a fluid, but not every choice for a possible tracer makes for a good tracer study. If you're looking for, solid, consistent, quantifiable results, you really need the ability to have a fluid marker that allows you to perform these accurate, very detailed mass balances of the tracer that you're introducing to and recovering from your reservoir. So a good tracer is one that meets certain criteria that allow you to avoid skewing that mass balance. At a bare minimum, they need to be something that doesn't degrade within your system. So you don't want to see thermal degradation, biological degradation, chemical degradation, or reactions. The choice for a fluid marker needs to be something that can be detected very quickly, very easily, and be detected at very low concentrations. And it shouldn't be masked by chemicals that exist within your reservoir fluid or might be introduced to it, and it shouldn't naturally sort of be in existence in your system. Since tracers are behaving as these sort of proxies for how your reservoir fluid are moving, their presence shouldn't skew the experiment that you're running. So you wouldn't want to use a tracer that has a chemical function or structure similar to a viscosifier or a friction reducer, anything that would actually change how your reservoir fluid would normally be behaving in the absence of tracers. And you'd want to have a tracer that passively follows the phase you want marked and not be lost to other fluids that might be present. So if I'm looking to measure oil movement in my reservoir, I wouldn't want my oil tracer to be lost to a gas phase. And I would want to make sure that my tracer was not moving faster or slower than the oil it's trying to mark. Finally, the tracer you choose should be safe, both for people and the environment at large. So with that criteria in mind, how do different tracer technologies available today compare? So let's start with that simplest case, with dyes, with pigments. The idea of adding essentially, something like food coloring to mark a water phase. Dyes, unsurprisingly, are not a great solution. If they were, we probably wouldn't have invested time and money into developing more complicated ways of marking our oil, water, and gas phases. Dyes generally don't prove to be stable over time at reservoir conditions, and their ability to passively follow a fluid phase is made complicated by the fact that they oftentimes will stick to or be absorbed by reservoir rock. Dyes are easy to detect. I mean, when you have a dye in water, for example, it's really easy to see it. But that signal they provide can easily be lost if you dilute them even to a few thousands few parts per thousand. So they are not an ideal type of tracer. DNA tracers are a very interesting technology because they actually have the ability to overcome that problem of a very weak signal. So if I have a sample, and in that sample, the presence of my DNA tracers are too minimal for me to normally detect, I have the ability to put them through a process where I literally am growing and multiplying that DNA signal until it can be seen. This is great because it lets you know, with some degree of certainty that your DNA tracers are present. But doing this upsets your ability to provide a more quantitative assessment of fluid flow because your mass balance gets thrown out the window when you start growing additional tracers and samples. In addition, DNA, like most biological items, tends to be degraded by temperature and runs the risk of either being absorbed or consumed by downhole bacteria. Nanoparticles and things like carbon dot technologies, these sort of man-made tracers that are unreactive and sort of lab-produced, are also very interesting technology. They are potentially going to be very disruptive to how we do tracer studies. But these are products that are still very much in the infancy of their development. It's a research subject I've actually been working on at Tracerco itself, and we've managed to file quite a few patents related to carbon dot technology in particular. And while it's very exciting for its potential, if you were to take a survey right now of what both industry and academia has managed to put out, you'll tend to find that nanoparticles and carbon dot technologies, they only really have a few unique signal types, and oftentimes these man-made tracers come with very high price tags and very short lifespans under reservoir conditions. What has been the real workhorse of the tracer industry have been chemical tracers. These can be delivered to your reservoir in a number of different ways. So sometimes you might directly add a liquid or gas chemical tracer. Sometimes you'll actually use a carrier material. You might take an absorbent particle, for example, and allow it to take up your tracer and then pump that particle into your well. Polymer enclosures are a very common way of doing this. They'll actually develop essentially a polymer matrix that encloses tracer, and your tracer basically elutes out of it into your reservoir. These are generally been the workhorse industry because of the fact that you can do a lot to validate tracers that you're using. A battery of tests prior to delivery or installation in your reservoir basically assures that your chemical tracers aren't prone to absorption or degradation. It validates that they don't partition across multiple reservoir fluids or fluid phases, and that they're detectable by well-accepted, well-known, commonly available tests like mass spec. Now, as chemical tracers dominate the industry today and appear like they're going to dominate for the near future, that's where we're going to be focusing a lot of the talk. We'll actually be starting with liquid tracers. Now, liquid tracers have classically been used for studies like interwell studies. Now, in interwell studies, you inject a slug of tracer into a well and then measure how and when those tracers start to appear in offset producing wells. What you end up measuring is fluid connections between wells for a better understanding of your reservoir geology. Subsurface flow in a reservoir tends to be anisotropic, and the reservoir oftentimes is layered with significant degrees of heterogeneity. And as a result, it's usually very difficult to accurately predict or simulate movement within the reservoir, especially in fields where you have lots and lots of injectors and producers. So what a tracer interwell study allows you to do is confirm the existence of things like flow barriers or fault lines, to quantify the extent of cross-flow between different zones, and to sort of ascertain the effectiveness of water and gas floods. The information you tend to get from a tracer interwell study is reliable, it's definitive, it's unambiguous, and thus it reduces uncertainties about the flow path, reservoir continuity, and directional features in the reservoir itself. Now, the data you would get from an interwell study tends to look like this. This would be sort of like the raw data from a offset production well. And what you would see is how the concentration of tracer observed in your produced fluid changes over time. Now, right off the bat, with a chart like this, you can pull away certain bits of information about your reservoir in a very sort of qualitative way. The first thing you can usually pull from a chart like this is when breakthrough of your tracer first happens. Now, this is obviously important, particularly if you're analyzing a water or gas flood, because it's telling you what's the shortest pathway, at least in terms of time, between your different wells. Beyond that, you can start pulling information about the peak of that concentration chart, what we call the mode. Now, what the mode is basically telling you is what is the most sort of common flow path or streamline of tracers tracing between the injector and the producer. The qualitative analysis you can pull from this are things like Well, if you have a peak that's very defined, very narrow in width, it gives you that qualitative understanding that most of your injected tracer is taking the same sort of pathway. This would be usually indicative of things like a very naturally fractured high communicative zone or potentially a thief zone. When you start seeing that peak widen, or if you see multiple sub-peaks, you right off the bat have some understanding that your tracers are moving through multiple competing pathways, each with sort of different streamlines for flow. How that tracer chart degrades is also terribly important to you, less for qualitative understanding and more for data analysis down the road. Now, as we are going to see in some of the slides coming up, when we come to actually interpreting our interwell data, a lot of it is very dependent on these time-weighted averages of concentration in order to make definitive statements about our reservoir. As such, it's really important to know how that tracer concentration is going to behave over the entire length of your well's life. The problem with most tracer studies is that they'll usually end long before your sample concentration actually hits zero in the production well. And a failure to include late-time data will oftentimes lead to an incorrect analysis, or at the very least, a skewed analysis. So to correct for that, we'll oftentimes take these charts and try and apply this exponential decline curve to behavior after the mode. And exponential decline curve is usually the most frequent or most common tracer decline observed. And that also reflects what we consider to be a normal reservoir. In most reservoirs, you tend to find that permeability will be distributed in a way that approximates this log normal distribution. And so with that sort of variation in permeability, you would expect to see a decline curve in your concentration charts. In some rare cases, you'll find that an alternate decline curve should be used. But those exceptions to the rule are very, very rare. And so I would really strongly advise avoiding them or approaching them with an abundance of caution. Finally, and probably the most important thing you can pull from this initial concentration data, is what we call the first temporal moment, or the mean residence time of the tracer in its path from injector to producer. So the mean residence time, the average time spent in your reservoir as you move along the fluid pathway, is central to calculating sweep efficiency, providing a measure of heterogeneity in the reservoir, providing a measure of permeability, all sorts of things. Off this concentration versus time graph, you can kind of eyeball where the mean residence time is, but data analytics are really a better way to sort of approach this data in order to get meaningful descriptions of your reservoir. And as we get into the math, we tend to find that there's a great deal you need to do to sort of prep your data for interpretation. Right off the bat, one of the first things you're going to do is take that raw data, take that concentration as it varies with time, and convert it into an age distribution function. An age distribution function tends to have units of inverse time, so inverse hours, inverse days, things like that. And it's an important conversion because it has several advantages over trying to work with your data in terms of concentration versus time. That age distribution function, that E of T, allows you to treat your tracer signal like a Dirac delta function, like a pulse, making it easier to deconvolute complicated systems. It's oftentimes easier to normalize, allowing you sort of a faster way of evaluating your flow system. And most importantly, it gives you a lot of advantages in fields where you're seeing some amount of fluid recycling. Now, if you are recycling your water, it is inevitable that you're going to recycle some of your tracer as well. And this age distribution function better addresses a tracer signal that's a combination of an original pulse plus recirculation. The mathematics of this sort of analysis have been pretty well established. They were originally developed for closed reactor vessels, but were modified for open boundary condition cases like a reservoir do work at U.S. national labs. So there's a great deal of information about this method that has been published and is freely available to anyone curious. So we have concentration data. We have this need to sort of convert it into a secondary function. And this is generally what you're going to see. This is sort of an example of concentration that's been converted to an H distribution function. Because we're dealing with a very simple case, you see that the H distribution function actually has an appearance very similar to our concentration data. And to the right, we have done that exponential decay curve fitting in order to forecast our late time behavior that would occur after our sampling. With this information, with this function, we can now start describing our reservoir in a lot of meaningful ways. Right off the bat, we can calculate our mean residence time. So we have some idea of how long it takes for fluid to move from injector to producer. And with that mean residence time, we're able to now mathematically calculate things like our swept pore volumes. And with swept pore volumes, we can sort of look at things like sweep efficiency. So if I'm doing a water flood or a gas flood, this is going to be incredibly critical information to me. If I know that my injected water flood is contacting 30% of all the connected pore volume in my reservoir, it gives me a very different picture of how effective that is than if my flood is moving through 90% of my connected pore volume. Beyond this, you can start using some of this data and data analytics to convert your concentration data into a description of your sort of storage capacity of the reservoir. You can look at heterogeneity, spread to permeability. There's actually a great deal that you can sort of do with this mathematically. In the interest of time, I'm forced to skip over a lot of this, but if you're interested, I suggest Googling temporal moment analysis to learn of all the things you can do with a data analytics and an interwell study. Now, beyond interwell, liquid molecular tracers are oftentimes used in hydraulic fracturing as well. I would actually say that they have been critical to the shale oil and gas boom in North America. Operationally, they're very simple to use. They're basically added like any other liquid additive directly to the frac fluid you're using to stimulate a given stage. So if you've ever been on a frac job and you've seen a liquid add system, you're not going to see something terribly different when it comes to the introduction of tracers. So liquid tracers are basically pumped on the backside of your pump trucks and into your missile and goes down with everything else you're pumping into the reservoir. Now, early in sort of the shale oil boom, you would see that liquid oil tracers were used predominantly in single well tests. They were used to establish just how much water, oil, and gas were being produced from individual stages, and quickly became the gold standard for quantifying stage production. But you found that with time, liquid tracers have been used much more really to look at interwell behavior, and that has grown in importance. Now you tend to see that liquid tracers are being used to do things like establish frac hits, optimize well and pad spacing, test whether or not diversion programs are working, and to compare different completion strategies. The process by which this is done is relatively straightforward. You're relying on a mass balance. So in this case, we're looking at our drainage volume and saying that at a certain point we have a barrier where the energy of pressure depletion and or any artificial lift no longer has the ability to mobilize oil, water, or gas. And we're basically saying now at the edges of that influence, we are behaving like this is a hard boundary and we have a true control volume. So for those of you who remember your transport phenomenon classes, within a control volume, the mass of chemical present is going to be dependent on what goes into the system, what you add, what comes out of the system, which you remove, and any amount that is generated sort of chemically within that control volume. Now, in a reservoir, we're not spontaneously creating new tracer molecules. So what we do instead is basically simplify that concentration to what is going in and what is coming out. And because we have a fixed mass tracer that we're introducing, it now behaves as a proxy for oil, gas, and water production. So if we inject a certain mass of tracer into stage 1, a certain mass into stage 2, a certain mass into stage 3, and then sort of normalize return based on how much we've added, we can now use that to basically assign the production of oil, water, and gas to different stages. Now, with water tracers, it's a relatively easy task. We are pumping our tracer alongside all the water we're adding, and it is hopefully marking it. So we're marking water that we're introducing in the pad. We're marking all the water in the slick water that's moving our prop in. We're even marking the water that's, just basically the capacity of the well behind our frac job. With oil tracers, it's a little bit more complicated. Now, with oil tracers, we're not adding hydrocarbons. We're just marking hydrocarbons in the reservoir. And the oil tracers that we use traditionally are not mobile in an aqueous phase. So to even get them into the reservoir requires a certain amount of chemical finagling. What we end up doing is that we take these oil tracers and set them up in a fairly unstable emulsion so that they can actually be mobilized and displaced by our frac fluid. So if we're pumping a slick water, we'll be adding this emulsion of oil tracer to our pad, and usually to the first 2/3 of our pumped proppant. We only do the first 2/3 because if you have something like a premature screen out, we want to make sure that all of our oil tracers in the reservoir and not captured and still mobile within the volume and capacity of our well itself. And as we're pumping this oil tracer, we will see it, since it's still relatively hydrophobic, sort of develop a skin on the outside of our pumped volume. So just like if you were adding oil to water, you end up with that sheen of oil on the surface because of the interfacial tension. Because it's emulsified, the fluid is still effectively moving it along with our frac fluid. But as we break reservoir rock and come in contact with the hydrocarbon that exists in a reservoir, the emulsification breaks and the oil tracer jumps phases into the in situ oil. And as that emulsification breaks, as we move phases, our oil tracer once again becomes immobile in an aqueous phase and is only really mobilized by an olive phase. So as we break new rock gets exposed to new hydrocarbon, oil tracer jumps phases, and we are left with a system that is now marking our oil but doesn't risk any chance of our oil tracer flowing back as they go to production and giving us some sort of false system or false measurement of production. Now, liquid molecular tracers are not the only way that we have used tracers in hydraulically fracked wells. Another very popular way is to use a carrier molecule, specifically an absorbent particulate. Now, the basic idea here is that you take something that is absorbent and allow it to basically soak up your tracer. And then when you are fracking a given stage, you can just pump that carrier particle alongside your proppant into a fracture. The absorbent carrier material, is now kind of trapped within your proppant pack, and then over time will release the tracer that has been infused into it into the oil or gas or water phase you're trying to mark as the particulate comes in contact with it. The big advantage here is that by having that slower controlled release, a lot of times your tracer study can have lifespans beyond what is achieved with oil tracers. With oil tracers, everything is mobile on day one. And so with very high production rates, it's possible that everything you inject could flow back sooner than you want. I mean, a study might only last weeks rather than months or years. With the particulate matter, because only what it's released is actually able to be produced, you can extend that lifespan. However, that particular benefit comes at a cost, namely that you no longer really have control on your mass balance. So going back to that in minus out plus generation case, generation is still zero. Out is known because you're producing it. What you don't really know, though, is how much tracer you're adding into your reservoir. This is because you can't really consistently know how much tracer is being eluted by your carrier molecule. Why is that? Well, that is because of two main problems. One comes from the fact that you have uncertain placement of your particulate tracer, and the other one is that you have uncertain surface area. Now, uncertain placement is actually a pretty easy problem to describe. Particulate tracers are generally seen as a low-cost solution, and to keep costs down, you tend to use a very small amount of these absorbent particulates. Earlier this year, the hydraulic fracture technology company, one vendor stated outright that they use 8.8 pounds of particulate material per stage, regardless of how big or small that stage is. So if I were to be fracking a typical well in the Wolfcamp, for example, I might be pumping 380, 400,000 pounds of proppant per stage, and that 8.8 pounds comes out to like 0.002% of my proppant pack. To sort of visualize that, I have over here dots that are representative of that proppant pack. We have 100,000 dots. 2 of those dots are red and would be representative of these absorbent tracer particulate style products. With the naked eye, you're not going to see those 2 red dots. Now, by exploding 100 dots square, you can see that those 2 red dots are actually present, but this gives you an idea of just how little of your proppant pack is actually tracer. And that gives you problems where you are at the mercy of localized flow effects. So remember, these tracers are only going to be released from the particles if the particles are wetted by the right type of fluid. So one that has absorbed water tracer is only going to release water tracer in the presence of water. One that has been infused with oil tracer is only going to release oil tracer in the presence of oil. So if I have placed these in the wrong spot and I have phase slippage in my fracture, you might see that your tracer is just completely bypassed by the phase that you're meant to trace. If you have damage because you didn't do a slick water, you did a cross-linked gel, and the gel didn't completely break down, and your tracer particles are actually being blocked by cross-linked material, that damage, that skin effect, might prevent your tracers from ever being wetted at all and releasing the tracer. There's actually a long list of things that could potentially go wrong, and just talking about the possible risks could have me talking for a while. But let's assume that you are in a best-case scenario. You have placed your carrier particles in the right spot. They are getting wetted by the right phase. In those situations, I should be able to quantify what's going on, right? I mean, I know the surface area. I know it's releasing a certain amount per time, except I don't. The material used oftentimes is irregular in size and shape, so I don't know what the surface area is. And a lot of times, your carrier particle is actually at high risk of breaking, of turning to fines. One of the most common carrier materials you will see being used by vendors today is activated carbon, the same sort of material that you might find in a Brita filter, though some higher quality vendors will use extruded carbon beads and things like that. They're very absorbent. I mean, they are great at soaking up tracer, and they will give you a nice controlled release rate, but they're also very brittle, and they have minimal crush strength. Putting them through some of the ISO standards for crush resistance on proppant, you tend to find that things like carbon beads have a K value on the range of about 2,000 psi. When you have a K value of about 2,000, that's basically saying that at 2,000 psi, 10% of your material is going to crush to the point where they're true fines. They're less than 44 microns. Compare that to the proppant that they're being pumped against. If I was looking at just regular old northern white sand, you'll find a K value in the range of 7, 8, 9,000. If you're using Texas Gold, Texas Brown, it'll probably be in that 7, 8 range. That tends to be a little bit weaker than northern white. But the point is that the proppant is 4 times less likely to crush than the carrier particles. At Tracerco, we realized that the proppant you're pumping actually needs that level of compressive strength. Like the overburden you're experiencing will crush weaker materials. And so we've taken the time to try and develop some sort of absorbent substrate that has a K value in the range of like 15,000, 16,000, that it's less likely to crush than the proppant it's being pumped against. But for the vast majority of what's out there, you're going to find that what you pump will oftentimes crush, will turn to fines, and as it breaks, you're going to expose more surface area downhole than your material had at surface. And you don't know how much it's going to crush, you don't know how much surface area is going to be exposed, you just can't quantify how large of an area can potentially be wetted and potentially be releasing proppant. So without that knowledge of how much material can release tracer, you can't really quantify your production coming in. Now, this is fine in a lot of cases. I mean, a lot of times you don't need to quantify your flow. A binary understanding of flow is occurring or flow is not is oftentimes enough. And it's just a question of what your goal is in your study. I know that sand control is not a real big topic in North America, but it's one of the areas I started in my career, and so it's close to my heart. And it's one of those areas where infused particulate tracers really, I think, shine. Consider the humble pre-packed sand screen. So these are sand screens where you have actually placed resin-coated proppant within the drainage layer. And these are oftentimes placed in your completion and are going to be covered up by a gravel pack. And the gravel pack is intended to be your primary method of keeping produced sand particles out of your well. And these pre-packed screens are a secondary level of control. The idea is that if your gravel pack is weak or non-existent above the pre-packed screens, the produced fines eventually will plug up the small interstitial spaces within the resin-coated sand, and that joint will actually plug off. You'll basically act like you're blanking off a section that doesn't have sand control. Now, imagine if I had placed particulate tracer particles within that drainage layer along with the resin-coated proppant. Now, as we have flow, I would see tracer, but as it eventually plugged off, you would see that tracer signal die off. This would give you that confirmation of not only where you were having a poor gravel pack, but confirmation that you had actually controlled it with your pre-packed screen. There's actually a lot of ways in sand control that I think particulate tracers can provide you a lot of information. If you follow ExxonMobil's example with non-aqueous gravel packs versus an alpha-beta gravel pack, you can use this to give you some idea of where you're running into problems. If you use shunt tubes, alternate path technology, this can give you some idea of where you're repacking your gravel pack and give you some idea of what geology is giving the biggest problems. And outside of those sort of conventional sand control wells, you might use this to look at, say, multilateral wells, basically to get flow assurance confirmation that different laterals are actually contributing, or look at packers and basically assure that your packer is holding and not allowing annular flow movement. So a lot of ways where particulate tracers can provide significant value by giving you that binary flow is happening, flow is not happening. But if you want quantifiable numbers, if you want to be able to say 600 barrels of oil is coming from my toe, 400 barrels is coming from stages 7, 8, things like that, you need to go to a liquid tracer technology in a hydraulically fractured well. Now, that's not to say that liquid tracers are the only way to get a quantifiable result. It's just really the only good way for fractured wells. For other types of wells, you can actually achieve a lot of the same benefits with polymer-enclosed tracers. Now, polymer-enclosed tracers basically are creating this polymer matrix that is holding your tracer material, and your tracer slowly elutes out of it. It just comes off at a fixed rate per square inch, square centimeter surface area. Unlike infused particles, these polymer-enclosed tracers have two big advantages. One, because you're installing them right at the well reservoir boundary, usually within the drainage layer of sand control screen, you know where they are in your completion and how far of a distance your tracer kind of needs to move. The other big thing is that your polymer rods, bars, whatever, aren't prone to crushing. So they have a consistent and known surface area over the life of the well. What that means is we can know how much tracer they're eluting over time as long as they're being wetted by the appropriate phase. So with that, it is possible to quantify production under the right cases. Now, we're actually going to start out by describing the wrong case, which is steady state flow. So picture a well. This well has only 2 points of entry, point A, point B, where we installed these polymer enclosed tracers. We're only producing water. Water can only come in from these two spots. Both those tracers are meant to mark water. Now, under steady state conditions, what do we know? We're going to see at surface, where we're collecting our samples, commingled flow from those two zones. Each one is releasing tracer, but what we're seeing in terms of measured concentration is this steady, consistent sort of signal. Because by commingling the flow, it isn't possible to sort of assign flow from one zone to another. The analogy I might use is if I had 2 shot glasses and I filled them with water and I had 3 drops of blue food coming to one and 2 drops of red food coming to another, and then I took both those shot glasses and mixed them together in a highball glass. If I handed that glass to someone and said, hey, tell me how much blue fluid and red fluid originally made this composition, you wouldn't be able to do it. All of your tracer is being diluted by that total amount of flow. So all you're really getting under steady state conditions is this qualitative knowledge that flow is occurring at all. To get a quantitative measurement, to be able to say how much flow is coming from one zone versus another, we have to consider a transient flow case. So this is supposed to have an animation. It doesn't appear to be working at the moment. So let's try something different. First, let's consider the same sort of case. We have a well. It's producing only from 2 spots. We've installed tracers there. But let's consider this well like it is initially shut in. So while it's initially shut in, the polymer rods at that well reservoir interface is still going to be giving off tracer. There's still completion brine. There's still in situ water. We're still releasing tracer at a known amount per unit of surface area per day. But because we are shut in, we're going to develop these sort of tracer clouds in that localized environment. Without that fast production flow, we're relying purely on diffusion to move tracers out, and diffusion is slow acting. So we'll end up with a cloud tracer locally, and it starts becoming more and more diffuse as you move away from the tracer. But when you bring the tracer online, and we will try sharing my screen so you can see the animation. Hopefully you are seeing my screen. As they bring that well online, what do we see? We see that cloud initially gets sucked into our well and get brought to surface. We see the cloud from the tracer closer to the toe getting sucked in and brought up to surface. And we see these plots of tracer where, initially you have your leading tracer, you have that slug kind of arrive, and you have it kind of die down to that sort of steady state release rate. You see the same sort of shape from the second tracer, but it's now offset. Why is it offset? Because for this tracer to arrive, first, I have to displace all the fluid that exists between tracer B and tracer A. What this lets me do is quantify that flow. So when I look at the time difference between the peaks, I know how much time it takes for me to displace that capacity of fluid between our tracers. And because we installed our completion, I know our IDs. So I have a fixed and known volume that is being displaced. So between the volume and the time, I can say what the flow rate is. I can say, hey, a certain amount of flow has to be coming from behind the tracer to displace that in that amount of time and get that tracer response. And so with that knowledge of the flow rate here, I can assign my flow, and I can basically take my total and subtract that out and get the assigned flow from here, and I can quantify just how much production is coming from different zones. Now, this is a simple case with only 2 tracers, but whether I have 2, 8, 30, it just ends up being the same process where I am subtracting out the contributions from different zones closer to the toe to get what my tracer is producing. Now, beyond that pulse velocity concept, there is another system known as the decay curve method. And this, again, mathematically is relatively straightforward. I'm taking those same tracer signals, and what I'm trying to do now is fit a curve to its exponential decline. And depending on how those decline rates compare, I can say certain things. If my decline rate is very, very rapid, then I know I have very strong inflow from that zone. If it's in between, that's sort of mid-level inflow. And if I have a very low or slow rate of decline, then I can say it's weak inflow. And if I have a flat line, then I can say that no tracer is coming and there's no inflow at all. By normalizing these decline curves and making them relative to each other, I can now have a ratio of inflow from each zone and compare it to my total production, and now start assigning that production to each zone and thus quantify what is coming along my wellbore. So these are some of the different ways that liquid chemical tracers and tracer technology in general is being used. And it's all math intensive, whether we're looking at Interwell, where we're trying to do, almost non-dimensional conversions, delta Dirac functions, and the like, whether we're looking at polymer enclosed tracers, where we're trying to use data analytics to do proper curve fits and comparisons, whether we're looking at liquid tracers in a fractured well, we're trying to do mass balance, all tend to be mathematically intensive in order to describe our reservoir. And that's where digital connectivity is really going to improve how tracer studies are being done in the future. Right now, you tend to find that tracer studies have a lot of the same data-related pain points. Right off the bat, you tend to have custom solutions that are really not fit for purpose. I am guilty of this. I'm guilty of this not just in this role, but in previous ones, where I tend to use Excel as my Swiss Army knife to fix any problem, and will develop custom macros and reports to do my analysis. This is problematic in and of itself, because when you try and use these sort of jury-rigged solutions, you create the potential for a lot of error. when I take my Excel workbook that is doing the statistical analysis I want to do and I hand it to a new employee, there's always the chance that new employee is going to modify it himself and pass it on to someone else. There's no consistency across versions. There's no version control. And if someone creates a mistake in their script or in their analysis, that also propagates down the line. These sorts of solutions tend to give you a lot of headaches when you're trying to deal with historical data. Anyone here ever had to search through a network drive at their company because they are looking at an old project and they know that there's a PowerPoint report and Excel workbooks kind of analyzing your data, and they're on the network somewhere, but you have to find it? I'm sure I'm not alone in this problem. It gives you issues with information security and data sharing. So again, when we're trying to do something not fit for purpose or trying to put it into a simple database or Excel-type spreadsheet system, it's difficult to protect that data. It's difficult to share it with other people in the company because large data files oftentimes can't be sent by emails. A lot of companies will restrict USB drives. You know, if you're trying to collaborate with someone on the other side of the world, getting information to and from them is difficult. And that's the simplest case. What if we're trying to share information, that raw data, to other programs? Let's say we're trying to use a tracer study and we're trying to feed that data into a reservoir simulator. Pulling it from an Excel file and trying to properly format the data for Eclipse, for CMG stars, for whatever your system is, a true headache. And inevitably, you end up in a situation where you're trying to find someone low enough on the totem pole to re-enter that data, which leads to the banality of data entry. There are issues of consistency of approach because if one person has created one customized report in Excel and with macros, that might not compare to what somebody else has put together. So if I am working with Tracerco in the Middle East, I would expect to see the same sort of analysis and approach in the Middle East as I do in North America or the North Sea or Indonesia. But a lot of times, not just with Tracerco, but with companies in general, where you don't have this sort of centralized data repositories, you tend to see inconsistent approaches as everyone kind of comes up with a localized solution. The final big problem with your data is this inability to connect the dots. When you have your data in these sort of siloed individual files, there's no way to really look at what the trends are overall. You know, if I'm an operator, and I've been working in the Permian now for 10 years, I might want to see some of the bigger trends, some of the things about what geology has generally paid off for me, or what completion strategies have generally paid off for me. But if my data is not sort of combined together in a way, I can see the trees, but I can't see the forest. And that's why I'm really proud to talk about what Tracerco has been doing lately. We've been trying to develop what's called our Insights platform. And what these are is a series of cloud-based tools to try and get over those pain points. It's a way of both watching a project develop operationally, being able to sort of play with your data on the fly, and have it in a secure place where you can now interconnect projects and even feed that data into other systems. I'm actually going to share my screen again and kind of show you some of what has been developed so far. So over here, I have an example project within our Insights platform. And right off the bat with this project, you have a home screen that will let you follow the project as it's going through the process. So you can review your initial project design. You can find out what the jobs actually occurred. And with this, you can actually see what the status is of samples. So if you are constantly having to track down a member of your vendor's sales team to find out whether samples have been arrived and been analyzed, if things are ready, this allows you from your cell phone, your tablet, your work computer to get that instantaneous data without having to go through an intermediary. You can actually see, which samples have arrived, which ones have been processed, which ones are reported, where they're from, all of that data. We talked about the difficulty in sometimes sharing large data files in a secure and safe way, this system allows you to do that too. Right off the bat, it has something very similar to what you might have experience with Google Drive or SharePoint. It gives you a place where you can upload documents and pass them back and forth between your organization and the company that is doing your tracer study, Tracerco in this instance. The nice thing about it is that those files are now permanently attached to the project. So if in the design of your tracer study you are reliant on certain log data files, certain maps, by uploading them here, not only do you get around a lot of company security concerns, but in the future, if someone comes to look at your project, they can always see those files because they're always associated with the project. And they can see sort of the mentality that went into why you made the decisions you did. You have your raw sample data as well. But what I consider to be one of the most exciting things is you have this ability to play with your data on the fly. So rather than relying on an Excel report, on PowerPoint slides, and hoping that your presenter has captured the right information, what this basically lets you do is analyze data on the fly, addressing what it is you want to know. So all your data gets sort of automatically fed into the system, and now you have the ability to sort of analyze it however you want. So let's say I want to look at, oil distribution along my wellbore and how that behavior is changing with time. And I want to see how it's changing over the first 2 months. I have the ability now to sort of create the views that I want. So here I'm looking at that daily production per zone of oil. Down here I have this sort of cumulative trend that kind of shows how that data is behaving. And I might see something that I find odd or interesting. Like I might find that, oh, hey, stages 8 and 9, which are geologically similar, should be behaving the same, but they're not. Why not? I can, go into my individual stage data. I can decide what it is I want to look at. So if in a presentation I decide I want to look at 8 and 9, I have that chart ready and available to me. I don't have to wait for a Tracerco technical employee to make that graph. I can make them on the fly, address what my concern is immediately, and very easily start to draw the story out of my data that I want to tell. If I want to share this with my boss, again, really easy to do. I basically give my boss permission, go to his office, pull it up on his computer. We can now talk through things. We also have the ability to have sort of back and forth commentary. So one of the neat things here is sort of the commenting structure, where I can take a graph or a chart that I'm looking at, put in a question, kind of flag it, and the counterpart at the operator, or if you're at the operator, the counterpart at Tracerco, when they log in, can basically see my question and click on it and see the exact same thing that I'm looking at when I put in the question. And then I could have, this sort of back and forth technical response, have it all documented, have it all available. I think it's very, very neat. And it takes away a lot of the uncertainty in security. It takes away inconsistent reporting behavior. It allows mistakes to be caught and updates to be pushed throughout the globe. It allows for very easy sharing of data from different groups within a company or back and forth between Tracerco and a client. Very, very neat. And beyond that, it has a lot of opportunities that I think have yet to be tapped because it's a brand new system. Namely, it allows for very easy data sharing across platforms. Hold on. So because all your data is now stored in the cloud, it is possible to have sort of limitless cross-analysis. If you're a geologist, if you're a reservoir engineer, and you're looking at improving your geological model or seeing fluid streamlines, custom APIs would basically allow you to pull your tracer data directly into an Eclipse, into a CMG Stars, into basically any program you want that has that sort of API structure to it. And now you can start comparing your tracer data to gamma ray logs, to simulation predictions. You can use them to fine-tune simulation predictions, improving things like your permeability estimates, your streamline estimates. Really, overall, I think it's a way to allow all sorts of new tools to come into it, including machine learning. You know, we were talking about losing the forest for the trees. Here's a way to have all your data available and start really doing deep dives into it. So not only can you tell sort of this flexible story with your data without having to wait for someone to get back to you, but you have the ability to now apply new statistical tools, new data analysis techniques, new machine learning tools, and try and pull out even more valuable information that you can now present to upper management, to your investors and the like. And I realize I've gone on a little bit longer than I intended to. So now is a good time for me to start taking questions.
Thank you, Dr. Banerjee, and we appreciate the very informative presentation. We did get a few questions from the audience, and I'll start with this. The question is, using controlled release tracers, what can be done to extend the life when dealing with high flow rates and high temperatures?
So when you're looking at some sort of solid material releasing your tracer, there's only a few things that you can do really to address that. Part of it is in pre-job evaluation. So when you are purchasing a chemical tracer, you really want to purchase it from a vendor that has done the appropriate work ahead of time, basically able to provide laboratory data saying, hey, my tracer will hold up to these temperatures without degradation and things like that. If they do degrade, there is some ability to correct for that mathematically if you can describe the degradation rate, but then you have to start using larger quantities of tracer to sort of compensate.
Thank you.
When you start talking about high flow rates, there's only a couple of things you can do. Again, you can always add in more tracer, but the cost adds up there. But one of the neat things that has been introduced to the industry lately has been the use of microencapsulated tracers. So this was a technology that previously existed in like the medical field and in cosmetics. Microencapsulated dyes for lipsticks, for example, were a big thing to try and make sure that bold reds stayed red, you know, all day, all night. And what you do there is you have a controlled rate of release as these sort of microencapsulated cells break down or release the tracer. And so when you're dealing with high flow rates, by using microencapsulation technology, you essentially are letting your tracer behave in a solid matrix like it's being replaced every month, every 6 months, every year, depending on how you fine-tune that microencapsulation.
Thank you. We have an additional question from the audience, that being, can the amount of completion fluid recovered be determined using tracers? And can we differentiate how much reservoir fluid is produced?
So it can be estimated. So when we're talking about completion brine, let's say, we tend to make certain assumptions that allow us to differentiate. So as we start returning water, the assumption is that what you're first seeing returned is your introduced completion fluids. Now, because we are quantifying the amounts, once you've exceeded that, it's assumed that what you're now producing after that is being marked by your water tracers, is reservoir fluids. So a lot of times you will see that this assumption holds up, and you'll see it used a lot, particularly in hydraulically fracked wells, to basically give you a measurement of sort of stage cleanup and fluid return. Now, can you say for certain that a given barrel of water was water you injected versus water that existed in situ? Not off of tracers alone. I mean, you can go a little deeper into chemical analysis and things like that to see if there's differences in the water itself. But if you have at least a ballpark idea of how much is being returned, you can get a very good idea of the level of cleanup and sort of draw that line between completion fluid recovered and in situ reservoir fluid being produced.
So thank you. An additional question was, can tracers determine reservoir complexity?
Yes. So particularly with interwell studies, you tend to find that this is one of those things that tracers kind of shine at where you have a lot of uncertainty. I mean, when you're going between your injector and your producer well, you have no idea really beyond a couple of feet what is going on down there. You have some ideas of what the heterogeneity is, but there's no way to actually prove it except through these sort of physical measurements. And so by doing an interwell study and by using some of those data analytic techniques I was talking about, it is possible to start looking at whether multiple fluid pathways exist, the level of heterogeneity, the most likely streamlines that exist between injector and producer. And these are oftentimes used to sort of validate what is built into a reservoir simulator and what you're predicting will happen. If your reservoir simulator disagrees with your tracer study, the tracer study is going to be right. That's a measurement of the physical world, and so your tracers really shine in that case.
Fantastic. I think we have time for one more, Doctor, if I may, before we wrap up. And we have another question. Any comments on gas phase, gas injectors tracers design, such as interwell mode or carbonate rocks?
Oh, all sorts of comments. So gas phase tracers tend to be some of the most complicated cases. And this is really where sort of experience and some of those data analysis tools, I think, are going to shine. Because of the fact that with gas, you are oftentimes dealing with multiple fluid phases. I mean, oftentimes you'll see, gas condensate next to, true gas. And the fact that the chemical structure of gas, when you're talking about methane, propane, butane, is very oleic and thus very similar to oil. When you're trying to create a tracer that is optimized for oil versus water, it's really easy because the chemical structure is very, very different. When you start talking about oil versus gas, you tend to run into a lot of the same sort of intermolecular forces, van der Waals forces, and so it becomes a little more complicated. Again, pre-job work becomes really important. So there are tasks to determine how much a given gas tracer is going to partition into an oil phase or into condensate. And so if you're dealing with a vendor, they should be able to provide you that data and say, look, this is how much is likely going to be lost to liquid phase condensate or to your oil phase, and this is how we are correcting our data models. And really, it ends up coming down largely to experience. If you are a company that has dealt with gas phase studies a lot, you will find that you are better able to handle the data, and it's just an issue of getting over the learning curve and making sure that you've done the appropriate laboratory testing ahead of time.
Fantastic. At this point, I'd like to take this opportunity to thank Dr. Sudiptya Banerjee and our sponsor, of course, Tracerco, for today's presentation, Understanding Connectivity, both Reservoir and Digital, how cloud-based software and digital platforms are modernizing tracer diagnostic studies. And as a reminder to our audience, today's webcast will be available on demand from the JPP website or using the same audience link provided. I'd like to thank everyone again for joining us, and we look forward to bringing you more webcasts in the near future.
Thank you all for listening. Hope you have a good afternoon.
There we go.